One of the things I really like doing when I'm at Discover is a conversation with Hewlett Packard Labs, and this year's no different. Kat, why don't I have you introduce yourself to everybody, and we'll jump into the conversation.
Sure. So I'm Kat Graves. I'm a researcher at Hewlett Packard Labs in Palo Alto.
And the reason I wanted to talk to you is because this morning you guys had a theater session, and your topic was neuromorphic computing. Neuromorphic, I think it means brain-like.
That's right.
What is it that you guys were sharing this morning?
Right. So we were showing our first prototype neuromorphic computing research that's called the dot product engine. And really what we're doing there is taking inspiration from the architecture of the brain in order to accelerate a vector matrix multiply.
So vector matrix multiply, and I know this morning you said something about that's kind of related to linear algebra, and I kind of used to think of myself as a math whiz. I don't remember a lot about linear algebra, but for people that just give a simple explanation, what does that mean?
So vector matrix multiplication, or just matrix multiplication, is really ubiquitous throughout just a ton of different algorithms and applications. It's used for filtering incoming images, in JPEG compression algorithms. Any kind of neural network layer uses a matrix multiply. All you're doing is bringing in sort of a 1D vector of numbers, and you have your computational kernel matrix, essentially, and you're multiplying that vector of numbers through sort of a square matrix of values to give you your result. So it's basically a lot of multiplications and additions all at once.
So what kind of applications could this have in terms of in the real world? And obviously we're talking about research in the labs, so it's a ways out. Help me brainstorm blue sky. What would this look like in the real world if it got deployed as a technology?
This is really a accelerator for a key component, this sort of math building block that we just use all the time. So you can think of it as more of an accelerator for things like machine learning and deep learning. And so it could be kind of like a sort of special processor that could go slot into the machine, for example. The machine, the way that it's structured, is so that you have systems on chips, specialized processors that are all talking to, that big pool of persistent memory. So, it could go in there and help just vastly accelerate a lot of these different applications. The other flip side to this is that it could also be used to connect to sensors and be doing local computation at, say, your phone, your Nest in your house, different kinds of IoT type devices. And that's because it's inherently analog already. So if you have an analog sensor, you even don't have to bother with the DAC, the digital to analog conversion, and save even more power doing it that way. So I guess I should say this because I didn't really mention it before. The reason you want to do this, why you would want to use the dot product engine or something like this to accelerate vector matrix multiplication, it's not just accelerating it, it's incredibly power efficient when you compare it to, say, a GPU or anything like this. So it's saving both time, but also really power.
And you've got one in your hand there. What are we kind of looking at when you open that up?
So this is the memristor component of the whole dot product engine vector matrix multiply. And so this chip here has many different sizes of those matrices. And so, we have everything from a 4x4 matrix up to a 128x64, which is that sort of larger rectangular one that you see here. And so we specially developed memristors at Hewlett Packard Labs to have that really nice analog capability and integrated them on this chip in those square matrices. And then there's a lot of custom hardware and software that we have back at Labs in order to actually do the vector matrix multiplication.
And when you talk about the size of the matrix, that gets back to what you were talking about before with linear algebra, because in linear algebra, there's specific matrices and there's rules around what those are.
Right, exactly. And depending on your application, you may want something more like a 16 by 16 matrix. For a lot of neural networking type things, your convolutional layers and stuff like this, your pooling layers can be about that size. Versus you could think about scaling this up, maybe in theory one day, to much larger matrices that are more useful for things like graph analytics.
So if I take this matrix piece home with me, what can I do with it?
So this is really part of our test bed. The dot product engine is at the point right now for for us to really test out different kinds of hardware, different kinds of configurations for how we do that vector matrix multiplication, these kinds of things. So actually this chip goes in a probe station. A probe card comes down and touches on pads in order to sort of talk to a specific matrix.
Yep.
Then we have custom hardware, PCB boards that are built in order to set up what kind of configuration communication we want to do to basically send the vector into the matrix that we want to do that multiplication for. And then even on top of that, we have software control, mostly in MATLAB, so that really most people in the lab can then program on top of it to then connect it to an even sort of higher level layer for handwriting recognition or stuff like this, and start doing baseline tasks with it.
So this seems interesting, but I feel like I've got a lot more to learn about it. So do you guys have papers that you've published now about this?
Yeah, so in fact, some of the architects at labs have already then said, okay, if I have this vector matrix multiply, what does that mean for how I want to put it together in an architecture? So that's an ISCAS paper out there from last year. And then one of our postdocs is actually presenting this week at the DAC conference, the Design Automation Conference, on that as well. And so that's available. And now that we've got our prototype working, several of us are also working on other publications for this. So stay tuned for even more.
So obviously, one last question to wrap it up. When you do this, you've got a team of people helping you. You're not the only person, but tell me how it felt like the first time you did it and it actually worked.
That was pretty good. And so I should mention the leader of our project is John Paul Strachan, and he came in over the weekend, debugging hardware, everything to just show that it could work and prove it. And it's just really fantastic because it's you get the proof point of the building block, and now you're at the fun part where it can be what do I then do with it?
Well, Kat, this is really interesting stuff. I enjoyed the session this morning. Thanks for spending some time with me now to go a little bit deeper.
Of course. My pleasure.